Hello everyone, in this short video, Max and I will be teaching you about how quadratic equations can hide themselves in everyday situations. In the following example, we will show you how a ball's trajectory can be mapped out by a quadratic function.
So, let's try to analyze this real-life situation. Hoang is standing on top of the stairs. He throws a paper ball off of the stairs. We will use the green line, shown here, to denote the horizontal, and we will draw a red arrow called V initial. This is the direction of the velocity the moment the ball leaves Hoang's hand. We will draw a yellow arc and name it the angle theta. And we will call the height that the ball starts at h, and the horizontal distance that the ball travels r. Now, since v initial is a vector, we can decompose it into the horizontal component of v, vx, and the vertical component of v, vy. The only acceleration on the ball currently is the gravity g, which points downwards for all objects. Since gravity only acts downwards, it will only affect the vertical component of v. So the horizontal component of v will stay constant throughout the entire flight. Now, one thing to note when doing these problems is to make sure to define a positive and negative direction. In this situation, we will define upwards and to the right as positive, and leftwards and downwards as negative. So for v, the horizontal and vertical components are positive. It is also important to note that h and r are both vectors, meaning they have direction. So h points downwards, so we define it as negative, and r points rightwards, so we define it as positive. Now that we're done analyzing the situation, we can get to the real juicy stuff, the math equations. So the first step would be to represent both components of v in terms of v initial, which is v initial cosine theta for the horizontal component of v, and v initial sine theta for the vertical component of v. Now, for step 2, we can apply two physics formulas. The first one should look pretty familiar. It's just the velocity times time equals the distance. Now, the second one, there is a proof, but it's kind of long and I don't want to get into it here. We'll just take it as true for the video. So in the end, what we want to do is combine these two equations. So let's try to substitute t into the second equation by writing t as r over vx. Now, in the fourth step, we just substitute t and we get h is equal to vy times r over vx minus 1 over 2g times r over vx squared. Now all we have to do is substitute vx and vy in and expand the parentheses. So we get h is equal to v initial times sine theta times r divided by v initial times cosine theta minus 1 over 2g times r squared over v initial squared times cosine squared. Now we just simplify and we can get h is equal to r times tangent theta minus g times r squared divided by 2v initial squared times cosine theta. And that concludes how you derive the trajectory formula. Now, something about this formula should look pretty familiar. There's an r squared term and an r term. That means that it's a quadratic equation. And with quadratic equations, to solve them, you can just apply the quadratic formula. So now let's try to apply what we learned into a real-life situation. Let's say that h is equal to negative 3 meters, theta is equal to 45 degrees, v initial is 5 meters per second, and gravity is 9.81 meters per second squared. We will rewrite the trajectory function into a quadratic equation where 0 is equal to negative g divided by 2 v initial squared times cosine squared times r squared plus r times tangent theta minus h. Now we just apply the quadratic formula and we will get r is approximately equal to 4.32 meters as the positive solution, which is the one we will take. It is important to note that this is an idealized version of the real world and we are neglecting air resistance and any other factors. In conclusion, the quadratic formula is really useful.